Welcome. Here are 10 themes in the foundations of mathematics, meaning logic and set theory. The same list has been presented last year in person. This is a slide version. The Gödel incompleteness theorems are astounding. They destroyed Hilbert's dream of a complete system for mathematics and also the hope to prove consistency within the system. The first incompleteness theorem assures that a strong enough axiomatic system is never complete. The second established that consistency cannot be proven within the system itself. Gödel essentially proved this sentence cannot be proven. Cantor's diagonal argument demonstrates that there are different infinities. The power set of a set is never the same cardinality than the set itself. Also for infinite sets. The numbers in the interval 0, 1, for example, cannot be counted. If one could count them, we could construct from this enumeration a new number. That's the diagonal argument. This new number is not included in the list. The CondorSchroederBernstein theorem is a tool to show that two sets have the same cardinality. One only has to construct two injective maps, one from A to B and one from B to A, to assure that there is a bijection. For example, the set of primes have the same cardinality than the set of integers, even though the primes are only a thin subset of the integers. Zermelo's well-ordering theorem assures that every set X can be well-ordered. This means that there is an ordering such that any non-empty subset of X has a least element. The well-ordering theorem follows from the axiom of choice, which in turn implies the Banach-Tarski paradox, a very strange statement that one can cut a sphere in Euclidean space into 5 pieces, rotate and translate these pieces, and to assemble two new spheres. And these two spheres then have the same size. Seemingly impossible, but it's possible using that axiom of choice or this well-ordering theorem of Zermelo. If we take the symmetric difference as addition and the intersection as multiplication, we get an algebra like the algebra of numbers. There's strange properties, however, like that a plus a is always equal to 0. But we can calculate with sets. This is called the Boolean algebra. Venn diagrams illustrate this. We see here the picture for the multiplication, intersection, and a picture for the addition, which is a symmetric difference. This is a ring, like the ring of numbers we are familiar with. The laws of thought are used when doing logical arguments. They go back to early philosophers like Plato or Aristotle. An example is that the statement is either true or false. There are rules to draw conclusions, like if A is true and A implies B, then B is true, or that if B is false and A implies B, then A is false, or then the law of identity, which tells that A implies A. Set theory is a universal language in mathematics. A function, for example, can be described as a subset of a Cartesian product space, and so is part of set theory. Already Dedekind has pointed out that mathematical structures can be expressed in the language of set theory. The algebraic structures, topological structures, order structures, measure theoretical structures, even fancy category theory. Another approach, foundation approach, can be described using sets. Bernhard Russell defined a set of all sets which do not contain themselves. Is this set including itself? It's a seemingly funny paradox, but it produced a crisis in mathematics. And it's based on the liar's paradox, which the Greeks already were aware of. I always lie. A barber shaves everybody who does not shave himself. Does he shave himself? That's what Bernhard Russell was, how he was popularizing this paradox. But it was a serious problem, and it needed some work to axiomatize set theory properly. The Cantor pairing principle implies, for example, that there is an equal amount of rational numbers, integers, they can be counted, or that the plane or space has the same cardinality than the interval 0, 1. We can count the points in our space using real numbers, or the interval. already Euclid reckoned that there are the same number of square numbers. And numbers, Hilbert has visualized this as a hotel. He's a manager of the hotel, which is fully booked. In order to accommodate more, he has just to send every guest n to room 2n. Now there is an infinitely many of rooms. You can also count rational numbers using a zigzag argument. Finally, we look at the extension of Gödel-Cohen statements which are true independent in the sense, and truly independent in the sense that both their acceptance or non-acceptance produces consistent model extensions of the original axiom system. Example, axiom of choice is such a case. This leads to a tree of mathematical theories where some statements are independent of each other, having the possibility to choose the basic mathematical framework, so switch on and off axioms, is very strange at first. So this is Paul Cohen, who has produced this theory of forcing in model theory. This is the end. Just a little bit of thanks. I liked the popular book of Hofstadter. When I was in high school, I enjoyed reading that, and then in college, the logic courses of Ernst Becker, they stimulated my own interest in this fascinating subject. That's it.